Hey, what's up? Welcome to the PoppySeed Dev channel. So today we're going to get started with our Merkle tree app. And let's go back. So it's going to be a file sharing Merkle tree app. And this tutorial is really good for intermediate Rust developers who want to basically build out an application of their own. If you just want to get started right away, here are the objectives. Pause the screen right now and read them through, and you can go right away. Otherwise, let's get started. So what are we implementing? We have the client and the server. Basically, what the client wants to do is it wants to upload all its files to the server, meanwhile delete them, but ensure basically that its files weren't tampered with. So what it does, it saves a Merkle root in a text file on its own, and uploads the files. Then when it wants a specific file, it can download it, and if it wants a proof that this file is indeed correct, it can basically request a proof that this file is correct. And to basically create this, we will have to use Merkle trees. So we're going to go a bit more deeper into that and how they work. And for any resources, if you want to get started, so you can always refer to the finished code on the GitHub. So this is the finished code. Or you can basically go to the documentation. So the documentation basically has a really good explanation of how everything works, how you can set up the project, and so on and so on. All right, let's get started. Okay, so you will open up your terminal and basically refer to the documentation as always, because we are lazy. So we'll do like a cargo new Merkle tree app and go into it. So this has basically created the binary, and we are going to basically create like separate crates for our client server and a library for our Merkle tree. So yeah, just paste that in, and this, as you can see, creates a really nice starting point, okay? And then basically what we're gonna do is update cargo toml, so to have something like this. This is our cargo toml like this, and then basically set up dependencies. So we go to our client cargo toml, setting up the dependencies. So what are we basically doing, right? We're using Tokyo and request, and then basically we're using Actix on the web, so to make our little application work. So that's basically it. But before we get started with the client and the server, let's go and start with our Merkle tree. So here's our Merkle tree. We're going to start with this starter code, and this code is basically was taken from the Polkadot Blockchain Academy. Special thanks for them, but it's a really nice basically base how you can get started with your Merkle tree. And if you just paste this in, here you'll have basically all kind of the overview of the documentation and what kind of steps you have to follow to basically get this working. And I provided some additional tests for you. So basically when you will be confident that your thing is working, you'll just run cargo test, and that's it basically. So let's get into an overview of how we can implement a Merkle tree and how Merkle trees work. Let's do a quick overview of how Merkle tree works. So Merkle tree is basically a binary tree where we have a bunch of leaf nodes and non-leaf nodes. And this structure basically allows us to verify a large data set by only knowing a small part of the tree. And if something changes, the whole tree basically changes. The root hash on the top changes. So basically we have a bunch of leaf nodes. In this case, these are representing the cryptographic hash of our files. And then we have non-leaf nodes that are these, that are basically, in this case, we will basically be calculating them by concatenation and hash of both of the hashes of the leaf nodes. So basically it represents a cryptographic hash of its child nodes. So how do we calculate Merkle root recursively? So this would be this function over here. So we have just a list of hashes. Don't mind this. So we have a list of hashes, and we have to output the Merkle root. So this is our large sentence. And in the case of if we are just calculating the Merkle root in the simplified way, we have to pad it. If we don't have 2 to the power of n, we have to pad it with additional like double quotation marks. And so what we do is move from the beginning and we go each layer deeper and deeper. So how do we do it? So we take our input. So for example, this would be a sentence, and each of these ABCD would be individual words. So, or in the case, it would be each individual file. So we would take A and compute the hash of A. So this would be a hash of A already here, hash of B. So these represent hashes, sorry. And A, so to go to a layer more deeper, we would basically concatenate hash of A and hash of B together and hash them again. And then same for C and D, same for E and F, same for G and H. And basically I, in this case, if we don't pad it, it's basically left alone in this layer. But if we pad it, it also gets hashed. So we move on layer and layer, and basically you can implement this here. Okay, great. Now we have our Merkle root. How can we generate our proof? So for generating our proof, this is here, you basically have a list of hashes and an index that you will want. So basically we will be generating a proof that this particular index, let's say index of 3, is actually, we can have a proof that this that the word in index 3 wasn't tampered with. So we provide a sentence plus an index and pad the base layer. So this is basically our normal proof, and provide the root and intermediate. So we have to our output has to be the root and intermediary nodes from which it can be reconstructed. So we have an array of inputs, and we say index, please provide generate a proof for index of 3. So this would be 0, 1, 2, 3. So this would be D. In this case, this black representation on our Merkle tree. So what would we have to do? Intermediary nodes from which it can be reconstructed. Okay, so this is its neighbor. So this X over here. So we can put it in our array, left hash C. Then we move one layer deeper, left hash AB. So we are here, and we are looking at this neighbor over here, and this is our left neighbor hash AB. It should be hash of A plus B, right? And then we go one more layer deeper, and we take this hash over here. So that's it. This is how we generate proof, and you can basically implement it yourselves. And if you get stuck, of course, refer to the code. Now for validating our proof. So our input basically is our root, our word, and our proof. So word here is the particular word that we want the proof to see if this word hasn't been tampered with, right? Or if this word is actually in our Merkle tree. So again, we are proving for if we have this kind of proof as we had before, this would be basically our Merkle tree again. And we basically take the reverse approach as we had when generating the proof. So if we have now root, so root is basically what we are comparing if the root is good with. So we take our initial word, and then we take our proof. So for the initial word, okay, we have D. We have D already. Okay, now we have to take left hash C. So we take C, and then we take, so we found this. We have just this now. Then we continue. Okay, now we are here. Okay, we have to take our neighbor and put it on the left. Okay, left hash AB. And now we are here, and we have to take right hash AFGH. Okay, and we take this. So that's it. That's basically how we validate our proof. And in a similar way, as I explained, you can write an algorithm to basically validate this proof. If you want to basically continue with a compact multiproof, you can go here, and in the implementing Merkle trees, you can scroll to the bottom and refer to the documentation. I don't want to keep this video too long. So next, let's go to the client and server setup. So first, let's do the basic setup. So we're going to generate some sample files. Yes, and I'm a bit cheating here because I started with my previous code. So we're going to generate some sample files, and so when they get generated, we are referring to the data, and this is basically file 1, file 2, file 3. Very simple. Then next, in the client documentation, main.rs basically has all the functionality. So let's check what we are doing. So main, what does it do? So it goes to the files, so it takes all the files that are necessary, it uploads and saves the Merkle root, deletes the files, and downloads and verifies the files. So in our upload file and save Merkle root, we upload all the files to basically our server. We're going to implement this later. And here we should actually, this is actually wrong. We should actually calculate our root directly on the client, with the client. So the client can basically save the Merkle root in a text file like this and have it basically safely stored for later. Then, next, delete files, basically simple implementation for deleting files. And then we have download and verification of files. So we download them from the server. And then, so basically this downloads from the server and gets the proof. So we get the proof from here. And basically check if the stored root is the same as the generated root, and if the responses match, and if the stored root is actually same as generated root, our files is actually verified and is correct, and basically nobody was tampered, the server wasn't tampering with the file, and if not, the verification fails. So let's check now basically our server code. Okay, so here we are using basically very simple, we create our app, and for this we are basically, if we check our cargo.toml, we are using basically Actix for this. Okay, so let's go to our main file in lib.rs. Very simple. So here how it works, we configure our services by having a root for upload, download, proof, and hello. So if you go basically to localhost hello, you can retrieve hello.world. So let's try this out. So great, by running the command cargo run manifest path server cargo.toml, basically we go to localhost 8000, and here you can see nothing basically happens because we have no root to this. But here if we type hello, we can get a nice return of hello world. Okay, amazing. So everything else is very simple. For the upload, we basically, what we do, we upload a file. The server stores it locally. So we insert every file, and basically this basically pushes the hashes, and we calculate the Merkle root and basically return it as a response. This step is actually not necessary for the server to do. It could be done by the client. So you can implement it a bit differently. So then if we want an individual file, basically this command just retrieves the individual file from the server. Very simple. And then the last one, we have basically, we can request a proof based on the individual file name. And what does it do here? What do we do? So we basically take individual files, we sort them. So we do like a sort based on their file names. And here we determine what is the index that we are looking for based on where it's located in the file names. And we generate a proof for it. So we take the generate proof function from the library we created, and we output it in the proof response as generated root and proof. So, and then as we had before, in the client, we can actually check if the file is correctly verified. So in the original documentation, you can basically refer to it and implement this structure yourself. And for testing and deployment, you can use cargo test to run individual tests. It's always good to have good unit tests, and some of them you can write yourselves. And for basically for checking if everything works as it should be, you can run the integration test. So you can have an end-to-end test script that you can basically, you can see here, and we already added it. So to add Docker, so the end-to-end test script is here. And if you want to add Docker to work basically to run everything seamlessly. You add Docker client implementation for running Docker here, and server implementation for running Docker here, and basically use Docker Compose to run everything together. And so yeah, and this basically runs everything. So let's check it out. All right, I had to stop the video here, but basically what you can check first, so when we run it, it basically initiates the server, it builds up the server, and then the client, and then basically we have the output here, and if everything was correct, it should say, okay, uploaded files, root, good, and then it deletes the files, it downloads the individual file, and then we check the stored root, should always be the same as the generated root, and the result basically should say, okay, this is the content of file 1, good, so blah blah blah, and it should say file 1.txt is verified, so this is correct, file 2 is verified, and file 3.txt is verified. Good. So if you get something like this, congrats, you build out the app. If not, you can always check my my original code. And thank you for being in this tutorial, and I'm happy to see you coding more. Bye.